Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here just doing some more Advent to Code. We're on day 14 of 2016. Again, if you're following along, I'd love to see your solutions. You can, I think you can fork a gist. So, look down in the description. I'll have my gist in there. You can fork it and put your own solution in there, and I'll see your fork. You can also, I think you can comment on gists too. So, love to see your solutions. Or yeah, just put stuff in the comments about how you did it differently or not. That would be great. So with that being said, let's push forward on this one. Day 14, one-time pad. In order to communicate securely with Santa, you're on this mission. While you're on this mission, you've been using a one-time pad that you generate using a prearranged algorithm. Unfortunately, you've run out of keys in your one-time pad and you need to generate some more. To generate keys, you first get, so this is like a security thing, right? Like a one-time pad can be very secure if you both know what the pads are. Yeah, like you see it cannot be cracked in cryptography. Like as long as both of you know the secret and you've shared it too securely, it's uncrackable. The issue occurs is like, how do you share one-time pads? So anyway, apparently they've come up with an algorithm to do it. To generate keys, you first get a stream of random data by taking the MD5 of a prearranged salt, your puzzle input, and an increasing integer index, starting with 0 and representing in decimal. Okay, so we've done something like this before. The resulting MD5 hash should be represented by the string of lowercase hexadecimal digits. Okay. However, not all of the MD5 hashes are keys, and you need 64 new keys for your one-time pad. A hash is a key only if it contains 3 of the same character in a row, like 777. Only consider the first such triplet in a hash. Okay, so we're going to look for triples in the hash, but only the first triple. One of the next 1,000 hashes in the string contains the same character 5 times in a row, like 7777. Okay, so it's a key if we find a triple and that triple has a quintuple in the next 1,000. There could be multiple triples though, so only do the first triple. Okay. Considering future hashes for 5 of a kind sequences does not cause those hashes to be skipped. Right. So this 555 actually become, or this 5 sevens actually could become 3 sevens in a future check, is what it's saying. Instead, regardless of whether the current hash is a key, always resume testing for keys starting with the very next hash. And then it gives us an example. If the prearranged salt is ABC, 18 has triple eights. However, it doesn't count because there's no triple eights in the next 1,000. The next index is 39. That gives us triple E's, and there is quintuple E's. None of the next triples. Eventually, though, this ID gives you your 64th. So using the example ABC, index 22,728 produces the 64th key. Given your actual salt in your puzzle input, what index produces your 64th one-time pad key? And this is my puzzle input. Okay. So I guess I don't know how many there are to check, but you don't want to recheck a hash, right? That does you no good. So one way to do that is to kind of keep a cache of ones that you've seen before. So that if you ever say oh, give me the 1,000th hash or whatever, it says, oh, I already know it, it's this. So you don't have to rehash. The way that I'm considering doing this though is like using a vecdeck where you like keep all the you like preload it with 1,000 and then you add a hash to the end of it and then you pop a hash off the back. So now you have, you know, the current ID plus the next 1,000 in your vecdeck. And so now you can do the math. You can say, does this have a triple? And is there a quintuple for that triple in there? Got it. Okay. Any key things? And I think I do that. So I can have this hash generator. We've done that before. Like we've used MD5 before, and we like kind of keep it in the outer part of the loop. So it's easy for us to generate new hashes, regenerate new hashes. The lowercase hexadecimal. I think that's just a format. Okay. Oh, let's see. How do I find the triples and the quintuples? For each hash, I'm actually only interested in what characters produced a triple, but only the first one. What is the first character for the triple? And then for the quintuples, I'm like, what characters produced quintuples? So if there's an E's and F's, I really just need E and F, right? So I can do that in like a hash set. So I can actually have I can have like a little kind of generator or whatever, a little function helper that like produces these values given a hash. To do that. Yeah, I think I might try that. Maybe we start with their input too. So say like let input equals ABC. Just so we can test it. What is my actual input? It's just a stir, right? Like that's what I'm actually going to be getting. So I can have this like helper function that's like get triple and quintuples. So you give me a hasher. I want it. I think it's going to be MD5 and the ID just like a U size because we're going to be counting up, right? Yeah, starting at 0. And then what am I going to give you? Oops. An option car. And then a Vec car. Like that. Like this will be the triple if I found one. And then this will be all the quintuples, if I found any of them, I think. So how does that work? So given a hash, I do hasher dot update id dot to string dot. We've done this before, right? Bytes. Is it like as bytes? I think it's like this. Like that. What doesn't it like about this? Oh, I haven't returned it yet. Yeah, okay. We'll get there in a second. So I now have my hash. So the question is, do I have a triple in there? So I think that's just like let triple equal hash dot as bytes dot windows of size 3 dot. We want to find the first one where W0 equals W1 and W1 equals W2. Dot map W2C or W0 as car, like that, right? So that'll give me my triple, I think. And we want to do the same thing for quintuple, but we want to do windows of 5. We can do something like w.iter.all C equals W0. So that's like check all of them, make sure they're all the same. Oh, but we don't want to do a find. We want to do a filter dot collect. And then we can return triple quintuple. Oops, like that. Make this mutable so I can take it over. Okay, I think that's right, right? I'm going to... You give me a hasher that's already like preloaded with the input, and then I'm going to call update on the ID that you give me. I'm going to hash it, find the first triple, map it and return it. And then I guess this is quintuples, find all the quintuples, right? So windows of 5, filter them where all of them are equal to the first, then map them to the first character and collect. So that gives me all my quintuples. Okay, so now for part 1, I need to I need my hasher. MD5 new hasher.update input. So that'll give me my initial hasher. initialized hasher. Okay, so now we need to fill up our window, right? So we'll be like 4, or no, we do this in a functional way. Like I want a vecdeck is essentially what I wanted the first 1,000. We can say like let window equal dot map I to, what did I call this? Get triples and quintuples. This is going to be hasher.clone. This is going to be I dot collect vecdeck of this. Do I have to specify it, or will it figure it out? Okay, so like that gives me my first 1,000. Now I'm gonna run my loop again. Now I'm gonna run my loop, I guess is what I mean. So it'll be like 4 ID in 0 dot because you just go for it. We're just gonna go until we find 64. So I need 64. So we say, okay, the first thing we want to do is add an item. So we should say window.push back get triple and quintuples hasher.clone. And it is going to be ID plus 1,000 because we already have 1,000 of them. So we're pushing back the next 1,000th one. Okay. So now we do let cur equals window.pop front.unwrap. We should always be able to pop front. Oh, but I can also get triple quintuples. So now I can say if let thumb triple equals triple. So like if this one has a triple, I need to check the rest of the windows for quintuples, right? I can say if window dot iter dot map quintuple q. Oh, I can just do filter right here, right? Oh, I should just do any. So if window iter any. So if any quintuple contains my triple, I do found plus equals 1. Oops. Why did I start at 64? Is that how, that's how many I'm supposed to go, right? Mm-hmm. It was stuck in my head. Return the ID. Otherwise, panic. Not found. What is this watch not working? This if can be collapsed. Oh, I can do and here. I don't use quintuples. Yeah, I guess not. I don't care about the 22, 7, 28. That is the right answer. So now we want to do it for our own input. So we just do this. Do that. 21903. Too high. Huh? Oh. I know what it is. Got to remember to trim. I think that's right. Oh, 31 seconds. Okay. Let's just look. Does this make sense? So we get our hasher. We create a window. It solves pretty fast, right? I like push back. I add a new one to my list and I get a new pop front, or I get a triple that I want to check. Now I can say, do I have a triple? And if I do, then I increment that I found one, do it by 64. Yeah, I think it's right. Like the issue was I wasn't trimming the new line at the end. Maybe you wouldn't have this if you just like copy and paste this into your puzzle input. I'm sure it would solve it too. Because my ABC worked, right? So that's what leads me to believe this is okay. We can actually wrap this in a little thing too if we wanted, I guess. Can we solve it now? Got it. It's the right answer. Of course, in order to make this process... Oh, I guess I should move on to part 2. Okay, so part 2. Of course, in order to make this process even more secure, you've also implemented key stretching. Key stretching forces attackers to spend more time generating hashes. Unfortunately, forces everyone else to spend more time too. To implement key stretching, whenever you generate a hash, before you use it, first find the MD5 hash of that hash, then the MD5 hash of that hash, and so on, a total of 216 additional hashings. Always use lowercase representations of the hash. For example, to find the stretched hash of index 0 and salt A, so you just keep hashing over and over 2006 times. So the stretch hash for index 0 in this situation is blah. In the end, you'll find the original hash. In the end, you find the original hash, one use of MD5. Then you find the hash of the previous hash 216 times for a total of 217 uses of MD5. So we're basically just going to do it, but we need to hash 216 times. Okay. So it's actually this function that changes. But this logic doesn't change either in P2. So I'm inclined to call this like find nth. And we'll give it an n, which is a u size. But then we'll also ask for a hash count, which is u size. So 1 will be find nth of input 64 and 1, and P2 will be no, oh, we should just do the number of extra times. So 216. So we'll call this extra hashes. So then we need to put that in here. Extra hashes. Extra hashes. And then this is just going to be n. And so now we need extra hashes in here. Right? So we always do it once. And then we'll do this, and we'll say 0 dot dot extra hashes dot for each hash equals. Oh, I got to do this whole thing. It does change it a little bit. This is not the end all. It's just going to be hash equals this. Yeah, this is not, I don't, why is this? It feels like this is stuck. I don't know why it is. Okay, so I'm actually going to do this and then do let hasher equals hasher clone. Hasher equals hasher dot clone. Oh no, this one I don't. I'm actually going to do new here. So I do think I can do this. Takes 6 seconds. Let me just make sure. Well, let's try it. That is the right answer. Okay, so that's part 2. I mean, yeah, so part 1 I don't think was too tough. Part 2, we're now hashing like a whole bunch more. And I think this logic is correct, right? So like for each extra hash that you want me to do, I'm going to create a new hasher, add my old hash, finalize it, and create a new hash. But it takes 6 seconds. So I am interested in maybe looking for any optimizations. I mean, it solves it, but it doesn't solve it super fast. So maybe we look and see how other people solved it. In Rust, link not very bright. Got stuck for a while. I didn't know she only had to consider the first triplet of the hash. Yeah. Oh, code is gone. I used a sliding iterator. Yeah, that's what I did. Well, I could reuse the hash. I don't know how much that helps versus like creating a new one. So like right here, we do this. And then we do hasher.reset. What doesn't it like? Okay, instead of doing it this way, we can do like 4 and 0 dot dot extra hashes. I guess I don't think it nets me anything if I have to create it. Yeah. So it may be because of the hash MD. I'm using a different algorithm. Yep. 3s, 5s. Okay. Yeah, I mean, I did it the same way as this person. Really not fast. I guess what I'm interested in finding is there some kind of like quicker way to generate a hash? Like, my guess is that's what's taking the most time. This one took 90 seconds in Ruby. $44. It doesn't seem like anyone has like anything that's taking quickly. I don't think there is. We could try looking for, let's see. I want to find something that's like, 2018. Sorry, I'm just Googling around. I don't know that it's helpful if you're staring at my Googleese. Oh, I can do this part. The first 1,000. No, not this one. Can I do this like into Editor? Saves me a second. I could do a bunch of them. So like if I say I'm going to do the first 30,000 in parallel, and then I only do if window.len less than or equal to 1,000. So I only do this part. So maybe I try and parallelize. Oh, there we go. That's much. But that's not the right answer. Windows iter take 1,000. Is that right? Yeah. Okay, so I basically just parallelize the heck out of this. And like, I mean, we can. We know it's going to be like some small, no, like, well, we know the answers, right? So we know it's never going to go past this plus 1,000. So I actually want to do like something like this. There you go. So the idea is like you say, oh, I'm going to parallelize this get triple and get like a whole block of them really quickly. Blup. And then I only need to update my window if I have less than 1,000, but I just keep popping and the key changes. You take 1,000 and then that lets you, you know, check for the thing. Okay. That was kind of a fun day. Wasn't too hard. Learned a little bit. Yeah, the first solution, I mean, 6 seconds is probably just because I'm running Rust. So like if I it looks like everyone used the same algorithm. So presumably, their time took about as much as mine. Just I guess it just depends on the algorithm speed and stuff. So anyway, let me know how you solved it. Any way to optimize it even further. That might be interesting to find ways to simplify and optimize. Otherwise, I think we got day 14 in the bag. Thanks, everybody. See ya.